Okay, so we are live. Hello, everyone. Welcome again to another Friday. Can you see the slides? I mean, let me just max this. Can everyone see the slides? Okay, cool. Okay, cool. Okay. Shall we just give it 1 minute or so, or 2 minutes, to see if more people will join? Because there are quite few people, like only few today. I wonder if there is another session, a webinar or something on Qiskit or something that some of the regulars normally attend. So let's just stay for 2-3 minutes. The session will be short today anyway, so don't worry, we will not overrun. Yeah. I will just take the opportunity. Okay, so you don't, Aditya is saying there is nothing going on right now. Okay. Yeah, let's just wait 1 minute or two to see if more people join. Because I've seen more people online before, just before I went. So I don't know if some people. Okay. So the CERN lecture. By the way, thank you for sharing the stuff on the chat. It seemed very interesting. The lectures. I definitely recommend everyone, especially those of you who want to get into quantum computing. Okay. So Ham is saying there is a quantum computing conference by University of Chicago. Okay. Well, let's give it 1 minute. If not, we'll just start. The others will probably watch it on YouTube, so it's not a problem. I wasn't aware of that conference, actually. So we have more people joining in. We have George has joined us. Welcome, George. Amir is also joining in. So for those who are just arriving, we've been waiting for you. Because we were wondering, the regulars, where are they? So we wait another 1 minute again. As I said, the session will be short anyway, so it will not overrun. So, it worth giving 2 or 3 minutes to see if more people join. By the way, have you filled the survey about the double session? So far, the answer seems to be most of you. If that's true, that's why we will take another poll today after the session. Most of you actually think it's a bad idea. So, so I'm assuming most of you want to carry on as it is, like 1 lecture per week, which is fine for me. I just thought you might want to box this foundation module before Christmas, but if it's not a problem. If your Christmas is also spoiled and you want to have like sessions during the Christmas period, that's fine. We'll carry on. Yeah, so Aditya is saying it's okay as long as they are Friday. Yeah, as I said, I'm flexible with the days. It could be Friday plus another day or another day, depending on the vast majority. And I only send the survey to you guys, the regulars, because you are the ones attending most regular live sessions. So it's only fair that you decide. So that's exactly what I will do at the end of this session. I will run a quick poll, so please stay after the session, and then we put it into bed, whether we will continue with the weekly stuff or you want double sessions. Okay, so let get started. I think it's gone now 4 minutes, so that's fine. Just before I start, can you all see the slides? Still see the slides? I hope so. Yeah, okay, cool. Thank you. Thank you, and thank you for your patience. Okay, so the the agenda for today is really this. It will be very short with just basic concepts, few concepts that we need. We'll first start with the pre-lecture comment stuff because I have some stuff to comment, and then we'll go to the concept of a transpose, matrix transpose. Then we'll talk about symmetric matrices and skew symmetric matrices. I won't touch, initially I was thinking to introduce Hermitian matrices, but I think they are probably, it's better to introduce them in the Hilbert space section, because then we can put everything more into quantum mechanics context. So yeah, don't worry, we will get to them in that section and the relationship between them and the matrices that we will be covering today, okay? So we'll also cover the matrix, the trace of a matrix, which I think a lot of you will know, but there will be some comments that you might find some interesting. And likewise, I was initially thinking to introduce the concept of a determinant, but I think it's better to do it in the next session, in the next section, because then it fits nicely with the matrix groups, you know, and these things about, you know, so we can show the relationship between invertibility of an operator and its determinant. So we will do that in the next section as opposed to doing it today. And then I will do study materials comments. We will have something new, a new test book, and there's a caveat to it. I will comment on that. And then we'll have like this double session poll just for you guys right now, those who are attending the live session, to decide whether you want to carry on with the weekly stuff or you want a double session so we can finish this module before Christmas. As I said, entirely up to you. It's not, if you want to carry on with the weekly stuff, that's fine. Okay, so let's get on with the foundation module. First of all, well done to all of you, especially the ones joining, you know, attending right now. You know, you've done very well, you know, so we are here. And to those joining or watching later on YouTube, this is where we are. The green stuff is the stuff that we went through. So this is the second part of this section here, matrix algebra. This is essentially like a lightweight intro to get you into a, you know, kind of into the zone. So when we get here, things will be much more easier. And when we get here also, okay? Another thing I want to comment is this section here, which is the next module, not next module, sorry, the next section. We will emphasize a lot in, rather than working in general linear group for any n, whenever possible, we will emphasize on you know, for n equals 2, you know, so for GL 2 of C, or, you know, UN of 2 or SUN of 2. So this is a unitary group and the special unitary group. This is, I think it's probably going to be better, like, you know, give you a better intuition if, you know, we work on these, I won't say toy examples, but, you know, like these, like concrete examples, though a lot of the results that we will, you know, cover will also apply to, you know, for, you know, n greater than 2. But nevertheless, it will enable you to build a better intuition. That way, in this section, in the quantum matrix of, in this section, we can go to higher dimension. When we are working with the Cn at higher dimension, we can then, you know, consider GL n of C, and UN U of n, and SU of n, okay? So that's just a comment that in the upcoming section, we will emphasize a lot on these two examples. Just check the chat. Okay, so I guess there's no question about these latest changes on in our foundation module. Okay, cool. We'll carry on. Just to recap, just quickly, because I know you know most of you already come across this. So last time we defined invertible matrices. Obviously, a matrix is invertible if it has an inverse, which we denote A minus 1, whose product with the matrix gives the identity matrix, right? And something I forgot to mention in the last session was that this is just, it's not a big deal, but it's nevertheless worth mentioning, is that the name for non-inverted matrices that we have no inverse is called singular matrix. So if you heard on the textbooks, someone say, let A be a singular matrix, or matrices with non-singular stuff, they mean this. So a singular matrix is a matrix that's not invertible, and non-singular is a matrix that's invertible. Okay. So in many textbooks, they will just tell you, A is non-singular or A is singular. Okay. So just so we are on the same page. And we also saw this proposition. I hope you managed to prove this, but I will say maybe if you have difficulties proving this, next week when we talk about the concept of a determinant, you will be able to prove this. So I will not go further on it until the next session. Another thing we cover is this notion of a diagonal matrix. So it's a matrix where all the entries except the diagonal entries are all zero. Right? We've seen these examples like this one. This is a bit, it's a diagonal matrix because the non-diagonal entries are all zero. Of course, it has a zero here, but yeah, it's still a diagonal. And obviously, when we talk about diagonal entries, we want diagonal matrices. When we talk about diagonal matrices, we want matrices with entries where not all of these elements are zero, of course, because if they are zero, then we have like the trivial zero matrix, right, which is boring. And there's also a proposition here that says, if two matrices are diagonal, then their product is also diagonal, and most important, very interestingly, they're also the two matrices commute. So I hope you were also able to prove this. And especially with this, you should be able to prove the other thing, the other proposition before. I should maybe have done the other proposition after this. So it says if a matrix, a diagonal matrix, if we have a diagonal matrix with the lambda i's as entries, then D is invertible if the lambda i's are non-zero. So, and we also saw in that case that the inverse of D would then be the inverse, the matrix whose entries are the inverses of the individual lambdas. So I think I need coffee because I'm already feeling a bit sleepy. Okay, so this is not a problem also, I assume. Let me just check the chat. Okay, no. So let's go to today's session. As I said, it will be a very short session. So the first definition we will go to is the notion of transpose. I hope I spelled it correct. And by the way, if you spot any a typo on the indices, not just on this slide, but on the other one, please let me know. So the transpose of a matrix A is essentially is defined as this. So you essentially invert. So you take the rows of the matrix and stack them vertically. So in other words, the rows of the matrix become the columns. Okay, so the first row becomes the first column, the second row becomes the second column, and so on. Okay, here's a toy example for for n equals 2 for m and for mn m2 of c. For example, these you can see. I hope I got it right. If not, please correct me. So you have these famous matrices that a lot of you on the audience certainly will recognize. So you have their transpose as this. And you will see now, I hope you already see something interesting happening here, with their transpose. Can you notice anything interesting? So let's say the X gate, let's call it just the X matrix in this case. So the transpose of it seems to be the same. Nothing has changed, right? If we hopefully I've done it right. Yeah. Is Z okay? Let's see. Does anyone think, okay, someone is saying Hermitian. We haven't defined yet Hermitian. Yeah, Z is diagonal. Yeah. Yeah. X is Hermitian. We will see that once we define the concept of Hermitian. We don't know what Hermitian means yet for us, but yeah, that's interesting. Let's carry on. You will see more stuff coming. Okay. So here are some of the properties. This is homework for you. That's why the session will be short, so you can do a lot of go and scratch your head with a lot of exercise. We are getting to a point where the more you do hands-on stuff, the better you get internalized with these concepts. So, given matrices A, B, and a scalar lambda, the claim is the following properties hold. Okay, so I'll leave this to you to prove this. Obviously, by going back to the definition, you look at what the definition of transpose, and in principle, you should be able to prove this. Okay. And another extra challenge I will have for you is that remember the definition of commutator. So like this, or if you want to be more formal, I would if you are a mathematician, a pure mathematician in algebra, you would write this. But nevertheless, just let's assume is this, okay? So the challenge is, go and compute the commutator of the the quantum gates that you saw previously, these guys, and then apply them to to the 0 qubit and 1 qubit, and see what happens. Maybe nothing will happen, but it's just a way of getting hands-on, and also try other combination, and maybe try to apply them to other interesting qubits. So that's your challenge. You check. Is AB? It's very interesting. We will get to that point, Amir. But nevertheless, it's actually an interesting exercise to see if there is any relationship if you cannot see it. But there will be something extra in the next few slides that maybe will help you consolidate all this your thinking into something more. Okay, so there is no, at this stage, this is all like very easy. There's no issues with the definition of transpose. You know what a transpose is, and obviously this will take time for you to compute. So, but I really recommend you, even before looking at solutions and these things, try to go through, one step by step, line by line, this is how you get these things into your head. Okay, though in reality, you have software and these things that does this for you, but nevertheless, it's very handy for you to be able to prove things like this. Okay. Okay, so now time to define, using the concept of transpose, we can define very interesting matrices with that. The first one is the notion of a symmetric matrix. So a symmetric matrix is a matrix that's equal to its own transpose. Okay, so here's a consequence of this definition, is that every diagonal, I hope you can see this, every diagonal matrix is symmetric, right? Do you agree? Yeah, okay. Yeah, so everyone agree, because something I forgot to mention is that the transpose does not change the diagonal elements of the matrix. For those of you struggling, let me go back again to slide just so you can see that, right? You can see is the matrix A is the transpose. So as you can see, the transpose does nothing to the diagonal, right? And then let's go back. Oops. So therefore, every diagonal is symmetric. You can see that. Well, this is the question then. Which which of the following matrices are symmetric? I will leave it as a thing for you, food of thought, you know. Don't assume, just a hint, don't assume every, you know, a symmetric matrix has to be necessarily a diagonal, okay? So although a diagonal matrix is symmetric, it does not say necessarily that, you know, every symmetric matrix is diagonal. Do you agree? Yeah, okay. So as a homework, I leave it to you or on the chat if you can agree amongst you know, to see which one is symmetric, okay, or which one is not, you know. And then a very interesting concept related to this, the concept of a symmetric matrix is this concept of a skew symmetric matrix. Or physicists normally, or mathematical physicists, they call this anti-symmetric matrices. So if you hear in some textbooks, some say anti-symmetric matrix, they means you know, skew. So it means the same thing. It's just you know, mathematicians use the term skew much more regularly than physicists. Physicists normally use anti-symmetric. Okay, so a matrix is skew symmetric or anti-symmetric if you are a physicist if its transpose is equals to its additive inverse. It's very interesting. And very interesting is also this theorem. So we won't call this proposition because it's a very interesting, these are very interesting results, so I will call them theorem. So it says that given two matrices A, B that are skew symmetric and given a scalar lambda, the following is true. So if A is invertible, then the inverse of A is also skew symmetric. Okay, and the second statement says the addition of two skew symmetric matrices and the commutator of two skew symmetric matrices are also skew symmetric. This is interesting because then it means that you know, the set of all skew symmetric matrices is closed under addition, right? And it's also closed under the commutator. In fact, later you will see that because of this, this is an example. Skew symmetric matrices are examples of what we call Lie algebra. We will get to that in the advanced module. Okay. Now the question is, which of these others are skew symmetric? Is there any of them that's skew symmetric? Look at the definition. So if it's skew symmetric, it means its transpose is equals to the matrix to the additive inverse. So you flip the sign of it, you have the thing. Okay. Is there any consensus? Is the Y gate, or sorry, the Y matrix skew symmetric? Is there a consensus? Yeah. Okay. So there is a consensus. If anyone, is there anyone who doesn't agree? Maybe anyone who is not able to see this, this is your chance to ask for clarification. So Amir is asking, are skew matrices a thing on their own? Depends on what you mean a thing. Can you clarify what a thing? What do you mean with a thing? Yeah, they, oh, so yeah, They do. That's why. That's one of the reasons I'm saying. Here skew matrices. They, they are independent. They are very interesting because they form a structure of themselves, like Lie algebra, for instance. Yes. I hope that's. If they form a structure, that's how I reformulated your point. They are interesting on their own, skew matrices, because they form a Lie algebra, and these Lie algebras are very important in both physics and also mathematics. Okay. Yeah. Skew symmetric. Yeah. Okay. Let's see. So let's see. Well, you can, it's you can, you can call them like, these. You can call it a skew symmetric matrix, or just, it's see. Yeah, just say a skew matrix or skew thing. Normally, when you see a skew matrix in some textbooks, just to save, it will be understood on the context that you mean is it's a symmetric, it's a skew symmetric matrix. Yeah. Okay. Okay. But please just go around these concepts and get your hands on with these things. It helps you internalize, and a lot of the confusion and stuff and these things will become a little bit more. You will have more clarity on your own, and we are getting to a stage where it's actually. It's of your benefit if you actually, as much as possible, that you are able to clarify the whatever confusion that you have by your own, by going through things again at home, or maybe, because that's the only way that you learn. Because if you're getting told every time most of the stuff, you will not remember. Only after you go through it, you get clarification on your own. That's the best way I see to learn these abstract concepts as we go around. Obviously, yeah, it's normal to especially when you get exposed to these things, to have some sort of confusion in these things. That's not a problem. Okay. So yeah, I claim you are able to solve this. To prove this, just go line by line. If any of you have any issues, ping on the chat, on the Gitter. And remember, ideally, I would like some of you to help each other before I come in. So if you have anything, I will not step in immediately. I'll wait until someone else on the channel, to see if someone else can help, because this is a way of you guys kind of showcasing what your knowledge. So, but if nobody can answer, then I can come in and help. And sometimes if I forget, please ping me, tag me on the chat, so I know that there's something pending that no one else has addressed. Okay. Okay. Okay, so another concept, very important concept, is that of trace. This is a very important, because later you will see, especially in the when you deal with the density matrix formalism of quantum mechanics, for instance, trace plays a very important role on how you extract probabilities and these things, So it's a very important concept. Anyway, given a matrix, so the trace is nothing more than just the sum of the diagonal elements, okay? So you take all the individual entries, you add them together, you get the trace of A, okay? I'm pretty sure that most of you already come across this. This is also very, very easy. And the claim is given two matrices and a scalar, the following properties are also true. Okay, so the trace of the transpose equals to the trace of the matrix itself. Okay, you will be able to prove this. I guess this is the most trivial thing because you know the trace, the transpose does not affect, as we saw, does not affect the diagonal of the matrix. So yeah, so it makes sense. And then these other properties. This is where it's not maybe not that intuitive, but again, if you go through the definitions of a product, I hope you already feel comfortable, doing the product. Maybe you can start with the concrete thing. Maybe you can M2 of C, for instance, and then maybe you can then generalize it if it's easier for you to see. But my claim is that you will be able to prove this. Okay. So now, a very interesting question here. We will not address why it's very important, but hopefully in the quantum section, when we reach the Hilbert spaces and the modeling part of quantum mechanics, this will come into play. You will understand it better. Can you see anything interesting happening here in terms of the trace? What can you notice? Something interesting here. What do these, in terms of trace, what do these operators have in common? Yeah. Yes. So Amir is saying, yeah. So they all have trace 0. That's interesting. You will see this is not a coincidence later. I won't say why for now because we don't have the stuff, the machinery that we need to be able to explore this. But this is very interesting. It's interesting that all the traces of all these guys, a lot of you, even those coming from quantum computing, already come across these operators. They have trace 0. Okay. So, but before we even get there, I will actually challenge you to go and scratch your head. Maybe look at other operators that show up in your in the test books, because I know some of you have been reading, quantum computing test books and these things. Look at all the operators that show there, and look at, maybe make a list of those that have trace 0, and see if you can kind of build an interesting list of them. We'll do the same with the determinants in the next sessions. Okay, so that's it really. Let me go back again actually before. So this session meant to be longer today because I wanted to introduce the concept of a Hermitian matrix, but I decided to last minute to leave that until we get to the Hilbert space section. Because then we can put everything, bundle everything together, with other things that machinery, other concept that you need, like orthonormal basis and these things, all packaged together. Because essentially this module, in fact, in quantum mechanics, there are two things, important things that you really need. Is like, in this case, because we are in finite dimensional Hilbert spaces, the two things you need is Hermitian operators, and you need unitary operators. That's all. In the next session and the next section of the module will be all about unitary operators and a kind of the special unitary group also, which is a subgroup of the unitary group. So it will be all about unitary operators and the special type of unitary operators. Okay. In terms of the study materials, I was a bit because a lot of the stuff that I cover are not kind of I couldn't really find them, because what we are now getting to a point where we need like a test book that's more tailored to the quantum stuff, right? So for the time being, maybe by the next session, I will find something. But for the time being, I will, just for a change, I will recommend this by Serge Lang, called Introduction to Linear Algebra. And it's a little bit more abstract, but this is, again, remember when I was talking about this section that, eventually the things will start becoming, even the study materials will start becoming more abstract, to be aligned with the online sessions. So this is a good way of you guys practicing a bit. And just, you can read, because it's not that lengthy book, it doesn't have that many, maybe 200 pages or something. But yeah, it also serves you for revision. You can review some of the concepts that we went through, some of the general concepts that we went through. So I really recommend this book. Now, the caveat is that I will not be able to upload it on the thing on GitHub, because I'm not sure about the licensing and these things. So what I will do, I know a place where you can get it downloaded. So I will email you the link. This is so that we don't, I don't want a situation where we upload this into GitHub and then we get, takedown notice, which is not nice. So I will email you the link to download this. And then, you go through these things, these pages or any other extra things to get you into the frame of mind once for us to start the next section. In fact, there's something I forgot to mention. Let me go back to the thing. First slide. I mean, to the so we will have 1 week break. Actually, this is by accident, because yeah. You mentioned Bourbaki. Yes. I believe he was a member of the Bourbaki group. I hope you enjoyed the newsletter, the story about the Bourbaki group. In fact, I think Aditya, you yourself, you replied on Twitter or something. Somewhere I saw that you mentioned. Indeed, they were the ones who introduced a lot of the concept that we take for granted. Nomenclature stuff like the concept of surjective. All these stuff, injectiveness, and all these terms are all Bourbaki. And the empty set, the symbol like that, they introduced that. There's a lot of things that Bourbaki introduced that we take for granted. Yeah. Anyway, going back to this, there will be, so next week, unfortunately, I won't be able to have a session because we have some internal things going on in the company, events, that like our annual board meeting and some meetings with about some projects going on the entire week next week. So I will be very busy. I won't have time. However, the week after, obviously, we will resume. That's why I think it will also give you an opportunity for you to review all these stuff, especially those of you who might be struggling with something. Go back again and review, because once we get to this section, it will be very, it's like a full speed. We are getting into the quantum stuff. We're going to get, into the, Hilbert spaces and all these other concrete, cool stuff, quantum related stuff. So it won't just be mathematics. It will just also be how, a little bit more on how these things are employed in physics and these things. It won't be a lecture about physics, obviously, but yeah, just to let you know, this will be more quantum oriented this part of the year. So it's good that you take 1 week. We take this opportunity of the break for you to go and revise. Really, get yourself into linear maps, linear operators that we went through. Go through the concept of group. These things. I will do some obviously I won't the way I will introduce it here, I will go like a step-by-step stuff, but it's very good. It's very important that you revise, because otherwise you will be you risk getting left behind, which is something that I really don't want. So yeah, does anyone have any questions? Okay, well, maybe after the poll, you have a question about, Amir is saying he has a question about Bourbaki. I can pull you after the poll, so you can ask me, you can ask the question if you want, or you can leave it to Gitter, it's up to you. So now the moment of truth. Let me just enable the Q&A. Let me do the poll. Please take the poll so we can decide this. We can put this into bed whether we'll have a double session or not, or we carry on with the weekly session as we're doing. Please do not leave until you complete this. I'm just creating the poll. I don't even know what to ask. Let me see. Do you want? Let me just make it very simple. Do you want double sessions? I guess it's the simplest way to ask. Double weekly sessions. Yes or no? Yes. No. Let's see. Okay, so the poll is now alive. I don't know if you guys can see. Okay. By the way, can you see the result of the poll? So, Okay, so let's see. Take your time to think it through. At the moment, we are like even. Okay, so no is has taken over. Okay. Yeah, the election results. Okay. Well, it's very close, but majority of you want to carry on with I assume want to carry on with the weekly stuff. They don't want the double. Okay. Let me just ask for those who want yes, who said yes. Are you also okay with carrying on with the weekly stuff? Okay, so one of them, there's another person missing, or two people missing. Does anyone else want to say? Okay with both, okay. Okay, in that case, let's, I guess we have, let's carry on with the weekly stuff, and then maybe, if some of you, in fact, this is something that if some of you then later want to do the weekly stuff, maybe instead of me initiating it, maybe you can, organize on the Gitter channel, make a poll and then tell me that, the mood has changed, So for the time being, I assume let's just carry on with the weekly stuff. The reason I suggested the stuff is that, I thought, you might want to do this before Christmas, but but it doesn't matter. Maybe even if you go over the Christmas period, maybe there will be just one session left. It's not a big deal anyway. And then we'll have like maybe a couple weeks, probably couple weeks of break before the advanced module, because I know some of you already indicated that you rather have instead of immediately starting with the next module, you would rather have like a break, which is something that I also agree, because I also need a break. I want to spend maybe 2 or 3 months traveling or something, especially after the lockdown. Yeah. So George is saying could do occasional tour session, but cannot commit to. Yeah. Ideally, we want like ideally I want like more like a regular commitment by the group like you guys online now, then just doing something random that with the risk of maybe there's no one showing up and then I'm like blah 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 with no one on the audience. So okay, so for the time being, I guess the vast majority, as you can see on the poll, at least the ones online now, maybe if I ask the other people, the ones, the YouTubers, they might, the result might be different, but I think that would be unfair because, they haven't been attending the live sessions. So there is no guarantee that, even if they say yes, they will be showing up. So, yeah. Okay. So this is one of the advantages of attending the live session because you can dictate, the schedule. So, yeah. Okay, so that's it then. Okay, so Soham, was there any question that I missed on the thing on the chat?
No, I think you covered pretty much all the questions. Yeah, I'm not seeing anything that was not answered today.
Yeah, Amir, there's just a question popping up. Yes, so we are not having a session next week. We'll have a break. So the next session will be, let me check the date. So the next session will be on November the 27th. I'll send an email to just to remind you of the next session. Okay, so Francisco is saying about the time issues. So that's another thing. Maybe we should have another poll just to help our friend Francisco, because it seems he is being affected by the time zone and he would like to start 1 hour later. Is that correct, Francisco? Okay, so let's create a poll. Would you mind, let's see, would you mind if we start 1 hour later? Let's see. Okay, so I believe the second poll is out. Okay, there's someone else again saying that would be an issue in the Indian time. Okay. Wow, this is very close. Okay, so there's someone. Okay. Okay, so most of you said no, at least once. Yeah, it's already pretty late. Yeah. Yeah. Okay. What about you, Soham? What do you think? Will this affect you?
Like I think it's fine if we stick to the time that we have right now.
Okay.
And like Francisco is saying that if he is the only one who is having the issue, then he will do the half on the YouTube.
Okay.
So that might
Okay.
best for everyone considered, I think.
Okay. 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 Yeah. So sorry for that, Francisco. uh, uh, yeah, it's just.
Though we could just begin it half hour later instead of 1 hour later if that works for everyone, then we
Yeah.
could do that.
Yeah. Okay. So it's complete.
Okay, so yeah, okay, I guess we can just stick to this time. Yeah, okay, all right, that's fine then.
Okay, that's yeah. It's fine. That's why I hate these these daylight time changes and these things. Obviously, when the clock goes backwards, we benefit from our side, sleeping 1 hour, but then it's like, yeah. Okay, catch the other part in the YouTube. Yeah. And you can also join the Gitter if you have any question, because the benefit, obviously, of attending this live session as opposed to watching it on YouTube is that you can interact with others. Okay. Than just watching. Yeah, that would be good with coming to the UK. If the place was not on lockdown, I don't think you want to come to the UK at the moment. I'm trying to escape, but I cannot escape because because of the lockdown. Okay. Yeah. So Francisco says he will be in Spain in Christmas. Yeah. So let's keep it this way as it is, and also let's keep up with the weekly stuff because most of you still want to do so, as opposed to changing. The reason I suggested the changes is because I thought, but it seems that I'm not the only one who will have the lockdown thing of Christmas, so you don't mind to have like sessions close to. So there's no shoppings and these things to do, right? Everything's like closed, so everything is now online. Okay, so is there any other question? Amir, did you say you wanted to ask something? Do you want me to pull you, or you can just, bring you on the thing? Or you can type it. Okay, so he said he's going to put it on Gitter. Okay, that's fine. So that's it then. There isn't much more I can say. And, remember next week there won't be a lecture session. There will be a break. And then the cool thing is we will start getting into the quantum stuff, the things that really matters to quantum mechanics, really. Well, not everything that we've done through is, also matters, but, because, the stuff that we will cover are built on the things that we've been covering. But nevertheless, this will be much more exciting for you guys. I believe anyway. So, yeah. And then we'll go to Hilbert spaces. And then we'll go to the quantum. This is like the operators, the concrete stuff, where we look at like case study stuff. We look at like, say, spin 1/2 system, for example, and then we look at the operators, blah blah blah. So yeah, and you will learn how to diagonalize a matrix, this type of stuff, so you can extract the eigenvalues and these things. You will learn why eigenvalues are important in quantum mechanics and these things. So it's really exciting, interesting stuff. Even though we are working with with the finite dimensional Hilbert spaces, still nevertheless very very interesting. But I think you will find it even more interesting once in the advanced module when we deal with the infinite dimensional Hilbert spaces, where the challenges are much more harder. So yeah. Okay. So yeah, thank you to George and everyone. And yeah, I hope you enjoyed, and please review, go back again to revise, take the opportunity of the break. And then, yeah, we see you again next in 2 weeks' time. Not the week after, not next week, the week after. And thank you to Soham again for helping. And we see you.
Thank you.
Catch up, everyone. Have a good weekend.